Probability, example 9. Mutually exclusive and not mutually exclusive events. So consider the probability of rolling one six-sided die and rolling a number less than 4 or a 6. So we can fairly quickly list the outcomes that are less than 4 or a 6. So less than 4 would be 1, 2, 3, and then a 6 is obviously a 6. We can by simply listing the outcomes and counting, we find the probability of rolling a number less than 4 or a 6 is, well, we have a total number of 6 outcomes. 4 are favorable, and that naturally simplifies to 2/3. Let me make that 3 look a little bit better. Okay, so remember when we were doing the independent events where we had and how we multiplied the two probabilities together. Now, we don't have an and on this situation, okay? We're not rolling a number less than 4 and a 6. We're rolling a number less than 4 or a 6. So this is going to be a little bit different operation. So they're asking us, do you think that we could come up with this 4, 6, or 2/3 using the individual probabilities of each event? Well, in this case, probability of rolling a number less than 4 is 3 out of 6 because you have the 1, 2, and 3. And we're not going to reduce this quite yet. I think you'll see why. What about the probability of rolling a 6? Well, there's only 1 6 on the die out of the total 6 outcomes. Can those two values be used to arrive at the probability of 2/3? In other words, what can we do with the 3, 6 and the 1, 6 to get a 4, 6, which becomes 2/3? And hopefully you're seeing that, could you add them? Yes, you can. And in fact, that's what you do, or generally will mean add, as we will talk about repeatedly. That's one of those things you need to remember. All right, so let's move up the screen a little bit. It says this time let's find the probability of rolling a number less than 4 or an even number. Okay, once again, let's list the outcomes that are less than 4 or an even number. So less than 4, 1, 2, and 3. Even number, I already have the 2. Okay, so then I don't need to list the 2 again. So 4 and 6, 2, 4, and 6 are even. So if I may add these, just write these individually. We had 1, 2, 3 for the less than 4, 2, 4, and 6. So I think you see that we have that 2 that's in both of those categories, but we're only going to list that once. So the probability of rolling a number less than 4, an even number, well, it looks like we have 1, 2, 3, 4, 5 favorable outcomes out of 6. And so they're asking us the question again, could I have come up with that using the individual probabilities? Well, rolling a number less than 4 is 3 out of 6. Rolling an even number, 2, 4, 6, 3 out of 6. So can you use these two to arrive at my 5, 6? Well, not just by themselves. I think we have a problem, don't we? And I think intuitively many of you could say, well, aren't you counting the 2 twice? Well, yes. So we can arrive at those values. We're just going to have to do a little something else. So I'm going to give myself some space here. And if I were to add these two, because or means add, what am I going to have to do? Well, what's the probability of their intersection, the intersection of these two sets, if you will? Well, there's a 2 that belongs in both groups, both categories. So the probability of rolling a 2 is 1 out of 6. So you see we have 3, 6 plus 3, 6 minus 1, 6, and there is your 5, 6. So can those two values be used to arrive at 5, 6? No. I would need to subtract probability of rolling a 2, which we will talk about in the next page. We'll have that formalized. So let me pause. All right, the first scenario on the previous page is an example of 2 mutually exclusive events. There are no shared outcomes between the 2 events, like the number less than 4 and the number 6. There's nothing they have in common. The second scenario's events are not mutually exclusive because the numbers less than 4, 1, 2, and 3, and even numbers 2, 4, and 6 have the shared value, so they have that 2 in common. So, for any events, A and B, the probability of A or B is the probability of A plus the probability of B. Now we could stop there if it was mutually exclusive, right? But to cover every scenario, we are going to have to subtract the probability of both A and B happening. Is there anything they have in common? What's the probability of that happening? We have to subtract that. So if the events are mutually exclusive and I need to correct this, it will be corrected on your notes by the time you get them. At least I hope they will be. I hope I don't forget because I'm just now catching this. And that's the probability of A or B. If they're mutually exclusive and they have nothing in common, I'm not going to have to subtract anything, am I? Okay? But every time you do one of these or situations, you have to ask, do they have anything in common? First of all, you need to remember that or means addition. Okay? Example 9. Suppose you draw a single card from a standard deck. What's the probability that you draw an ace or a jack? You have to ask yourself, okay, or means plus, is there a jack of aces or ace of jacks? No, those are mutually exclusive events. So the probability of drawing an ace is 4 out of 52. Probability of drawing a jack is 4 out of 52 because there's 4 of them, just like the aces. And that gives us 8 out of 52, which reduces to 2/13. All right, B, what's the probability you draw a red card or a face card? All right, or means add, and we're going to have to ask ourselves, are there any cards that are both red and face cards? Yes, so this is not mutually exclusive. So let's go ahead and add red, probability of drawing a red card, plus the probability of drawing a face card. There are a total of 12 face cards. And then I have to subtract from that the probability of drawing a card that is both red and a face card. So that would be the Jack, Queen, King of Hearts, Jack, Queen, King of Diamonds. So there's 6 of them. All right, so that will give us 32 over 52, and then that reduces to 8/13. Okay? What's the probability you draw a club or the Queen of Hearts? So again, or means add a club and Queen of Hearts. So by very definite definition, Queen of Hearts cannot be a club. So the probability of drawing a club is 13 out of 52. Queen of Hearts, well, there's only one of them. 1 out of 52. That yields 14 out of 52, and then that reduces as well. What's the probability that you draw a diamond or a king? So or means add. You have to ask ourselves, is there a card that is both a diamond and a king? Yes, we have the King of Diamonds, and there's only one of them. So how many diamonds are there? 13 out of 52. How many kings are there? 4 out of 52. And then let's subtract that probability of that one King of Diamonds being drawn. Okay, so that gives us 16 out of 52. And then that reduces to 4/13. Okay, what's the probability that you draw a black 7 or a red 9? Or means add. So cards cannot be both black and red, so we can tell right there that they are mutually exclusive. So black sevens. Well, I've got a club of 7 of clubs and a 7 of spades. So that's 2 out of 52. And a red 9. So I've got a 9 of hearts, 9 of diamonds. That's 2 of them. And that's 4 out of 52. Which gives us 1 out of 13. Okay, what's the probability you draw a black card or an ace? Okay, how many cards are both black cards and they're also aces? Well, we've got the ace of clubs and the ace of spades. All right, so what's the probability of drawing a black card? 26 out of 52. An ace, 4 out of 52. Let's subtract the ones that are both black cards and aces. Probability of that happening is 2 out of 52, which gives us 28 out of 52, which is 7/13.